Hello everybody, these are the notes for 4.1 and 4.3. This opens our work on trigonometry. We're going to start with some definitions here, and you can see them on your screen. Please feel free to write as I talk. Our first definition here is an angle in standard position. This will be our default, how we describe angles going through the unit. They will have a vertex at the origin, and the initial side of the angle, the starting point of the angle, in other words, will start on the x-axis. From that point, we will work counterclockwise around our coordinate axis. We will also work extensively with reference angles. This is the angle formed between the terminal side of an angle and the x-axis. Just for a point of reference, this should always be less than 90 degrees. That is actually a big part of why we like reference angles. We can use what we know about angles basically from 0 to 90 degrees. We can use what we've done before with right triangle trigonometry using a reference angle. Coterminal angles are just like how they sound. They're angles that end in the same spot. They are separated by multiples of 360 degrees or 2 pi radians. Hopefully this makes sense. Then next we go to the conversion between those two forms, between those two units in angle measurements. If we want to go from degrees to radians, I take my degree amount, whatever it is, and I multiply it times pi over 180. The result of that multiplication will give me the radian measure. And working in the opposite direction, multiplying radians times 180 over pi will end with our degree measure. Things get a little bit more complicated with degrees. We're going to go a little bit further, a little bit smaller measurements within degrees. So within degrees, we have each degree is made up of 60 minutes, and each minute within a degree is made up of 60 seconds. If it feels a lot like time, I think you should trust your instinct on that. So what we will see is conversions between degrees in decimal form and degrees with minutes and seconds. So we can do this with our understanding of fractions without a calculator, and then we'll show you a little bit with a calculator. So if I wanted to convert negative 121 degrees 45 minutes, one part of this will be identical. The negative 121 degrees will not change. What will change is we're going to move from 45 minutes to decimals. So 45 minutes is really 45 out of 60, which we could simplify down to 3 over 4. So we would write that as a decimal as negative 121.75 degrees. I'd like you to go ahead, pause the video, and try B and C as well. On part B, you're converting 48 degrees, 24 minutes. And then on part C, you're converting 120.1 degrees into minutes and seconds. So go ahead and pause the video. I'm going to work these out, and we'll talk about our answers. All right, so here's my work. On part B, we had 48 degrees and 24 minutes. I converted this to kind of a mixed number. I have 48, and I guess there should be a plus sign in the middle there. 48 plus 24 over 60. That is a fraction we can simplify down to 4/10. So our final answer there would be 48.4 degrees. On part C, we have 120.1 degrees. And what I'm really trying to do is convert this 0.1 to a fraction with 60 in the denominator. So I jumped from 0.1 to 1/10 and then scaled that fraction up to 6 over 60, getting us to our final answer of 120 degrees and 6 minutes. We can also convert with a calculator, and we can do basically the same thing we did just up above. We can express our minutes as a fraction with 60 in the denominator, and our seconds with 3,600 or 60 times 60 in the denominator. In other words, every degree has 60 minutes and every minute has 60 seconds, so that every degree will have 3,600 seconds. All we need to do is add these fractions together in our calculator, and I'm doing this off screen, but I'm getting an answer of 342.119 degrees. This is using our calculator, just using fractions and converting. The other way, we can actually use our angle menu. If you're looking at the middle of your calculator, there's an angle button, and then there is a convert to DMS button, right? So I have that written there in our notes. But what that'll do is it'll take a number and convert it into degrees, minutes, and seconds. We could enter exactly like we see here, 342. So I go to my calculator and I type in 342. And then I need to go to my angle menu. I'm going to hit second, and it's the apps button. And then I'll select the degree sign. Next, I'm going to type 7, and then again, I'm going to go to second and go to my angle menu, right, entering through the apps button. And now I have minutes there. In order to add seconds, I'm going to have to use the quotation marks that you see on the bottom right-hand side of your calculator. They're actually the green alpha kind of shift key attached to the plus sign in the bottom right of our calculator. So I will hit alpha and the plus sign, which will get me my quotation marks, which also stand in for our seconds. Once I have that entered into my calculator exactly like we see it, we can hit enter, and it will convert it to decimals. Again, this is the same one we saw up above, so we will still get the same answer, 342.119 degrees. Going the other way, we would type in our angle, negative 43.2076, and then I would hit second and the apps button to get back to that angle screen. And I would choose, sorry, that looked a little strange. There's an arrow to DMS. It will convert directly to degrees, minutes, and seconds. And what we will get as a result for this problem is negative 43 degrees, 12 minutes, and 27.36 seconds. We're going to move to page 2 now. This will include some new formulas. So these formulas are all related to traveling in a circular path. So the first thing we'll be able to find is the length of a circular arc. That is used as letter S here, times r times theta. R is our radius, and theta is our radian measure. Just a note here, while we use degrees and radians somewhat interchangeably in trigonometry, when we're dealing with this formula in particular, we must use radians. Moving from there, we can move along a circular arc at a certain speed. So if I wanted to find the linear speed, I need to take my circular, the length along the circular arc, my distance, and divide it by time. I can also figure out an angular speed. Basically, this does not take into account the length of the radius. So angular speed is how fast we are spinning. If I am if I have a very long radius, my linear speed will be much slower than if I had a very short radius. What's different about angular speed is that it does not matter the length of the radius. All we really care about is how fast we are spinning. So what's the big difference here? Our formula does not contain r. Instead, it is simply theta, our radian measure, divided by time. And finally, we can convert between linear speed and angular speed. Linear speed can be represented as our angular speed times the radius, or the radius times theta over t, which is, again, just our angular speed. So there's 3 examples at the bottom. I'm giving you guys the formula that you should use to start each problem, but I'd like you to pause here and try these problems on your own. I'm going to pause my own video, work these out, and kind of discuss things to be careful of as you work through them. All right, team, let's see how we did. So on the first one, they tell us that we have a circle with radius 10 inches. They want us to find the length of the arc intercepted by a central angle of 120 degrees. So my equation that I need to use, the measure of a central arc, the length of an arc intercepted by a central angle, times the radius times theta. What I have over here on right is the most likely source of mistakes. We need to convert to radians, even though the problem gave us our work in degrees. What I need to do is take that 10, my radius, and multiply it times my radian measure. 120 degrees is 2 pi over 3 radians. So the length of the arc intercepted by that central angle will be 20 pi over 3 inches. On example 2, they tell us that we have a central angle theta is in a circle with radius 12, and that this radius intercepts an arc length of 42 feet. So what we need to figure out is the measure of angle theta. So we plug in what we know. We know that the radius is 12, and we also know that the arc length is 42. That's our S quantity. So all we really can do is solve for theta. We're working backwards, we divide, and that 7 over 2 radians, well, first of all, it has to be radians because that's how this formula will always work. But 7 over 2 is our radian measure. We're finding a component of this formula, not always the arc intercepted by an angle. Finally, on 3, they tell us that a wind machine is used to generate electricity with blades that are 10 feet in length. That 10 feet I am using as my radius. Excuse me, let's keep that color-coded. As my radius. They also tell us that the propeller is rotating 4 revolutions per second. We need to use that information and convert that to an angle measure in radians. So what I do know is that a full rotation is 360 degrees or 2 pi radians. So what I did is I took 4 revolutions per second and plugged in 8 pi over 1. 8 pi radians, right, 4 revolutions per second divided by 1. I multiplied those quantities together, 10 times 8 pi, and I got my linear speed of the tips of the blade is they are 80 pi feet per second. And we are done.